Okay, so the last factor that can change how fast a reaction occurs is called a catalyst. So again, you probably have heard that word used before. And again, those of you, especially those of you that have taken um, biology, because enzymes are biological catalysts. So the big difference between a catalyst and a reaction intermediate is this line here. Catalysts are not used up. So, which makes sense because generally speaking, catalysts are often expensive. So if they got used up every single time, then their usefulness, increasing the rate of reaction, would start to decrease. So for example, if you're into cars, you may have heard of a catalytic converter, and those are often precious metals like rhodium or palladium. They're very expensive and they help to make the reaction happen faster in the car. So you can imagine that if it couldn't be regenerated, and every single time you drove your car, every single time the combustion reaction in your car occurred, you needed to put in a new catalyst, then the price to run a car could be way, way too high. It would be less practical than it is now. There are all kinds of cases in the industry where we use catalysts, things like sulfuric acid, which is a common organic catalyst, so maybe you'll remember that from that unit. Even the enzymes inside our body, if we couldn't reuse those, your body had to regenerate these huge molecules every single time. That would be a big toll on the biochemical reactions that occur inside our body, how complex and energetic we get to be, and how often you would have to regenerate those could have a big impact as well. So they think that a catalyst lowers the activation energy so that the reaction can happen faster. So again, sort of think of it logically. If you lower the energy required, then less time would be required. And the way they think that it lowers the activation energy is provides an alternate mechanism. So we're going to look at it graphically in a second, or using a diagram in a second. So you'll notice some things on the diagram. The delta H value is the same. So where the original products and reactants are doesn't change, just how the alternate mechanism. So what that means is, it says different elementary steps, like more than one. So the same principles like we just talked about. So if you look at the picture in the note, it's got two peaks in the catalyzed reaction, which means two steps. Okay, so if you are a colorful kind of person, then what I would do is, you could even do it with a highlighter. These two lines it's hard to differentiate between them because it doesn't photocopy in color. So you can remember the reactants and products are the same. I'm going to do the catalyzed line in bright green. So it has lowered the activation energy. So you can see it is lower than the one peak. How much lower? Again, we're not going to do it to scale. Just make sure that I know that you know that it's lower, okay? And it has to be more than one step. So in this case, they've chosen 2 steps. So maybe, so the mechanism provided only has 2 or whatever, okay? So this is just really in general. Okay, so the overall peaks must be lower. Again, how much lower? That doesn't matter. Just make sure it's lower, that I can see it's lower. And there has to be more than one step. So if you're not given more than one step, you could draw, like you could draw as many as you wanted to, okay? It doesn't really matter. It just has to be more than one, and overall, it has to be lower. But it starts and ends in the same spot. Okay, so another diagram we did with energy. So what I want to just do is just totally make a sketch, okay? So in 6.5, we did Maxwell-Boltzmann's, which were the normal distribution one. So just, if you don't have a lot of space, don't worry about it. Just make a little sketch. The big thing is that energy was down here and the number of molecules was on the side. And it looked like this ish, something like that. It doesn't really matter. And because it was kinetic energy, we called the minimum, does anyone remember? Starts with a T. So if you want to remind yourself that EA is the minimum PE, or potential energy, that is one thing that students do find frustrating. We're switching back and forth, potential, kinetic, yes, I know. Okay, so you have to use your math brain a little bit. If a catalyst is going to lower the energy required, and this is the minimum energy required. Remember now, in this distribution, this line here is how many molecules. It's not energy anymore. So some people, what they'll do is, please don't write this down. Some people, when they're given a Maxwell-Boltzmann distribution, will do things like this. If a catalyst is added, but this line does not represent energy. Which line represents energy? This one here? So if it's going to lower, would it go this way or this way? This is a graph, 0, right? So it would go this way. Once you draw the new line, then you can see in the picture, oh yeah, a lot more molecules now have enough energy to react, so that reaction would be faster. It actually does make sense. So there is important differences because this line here does not represent energy like it does in this one. I wrote it as more area under the curve for my calculus friends because, actually physics too, you guys probably calculate area under the curve related to the derivative, stuff like that. So moving forward, again, if you take pure sciences, calculus is an important requirement. To do the actual math, to not just do it, in general, not to scale, etc. Okay, so let's say you have a mechanism. So you can do the same sort of thing as we did before. We're going to cross stuff out, but now we need to distinguish between catalysts and reaction intermediates. So I'm going to have like two sides. You can use different colors if you want, it doesn't matter. So reaction intermediates are crossed out or they're canceled out. I'm going to try to save room. If I say R, that means reactants, P means products. That's okay? Okay, so that does not distinguish between them, right? That is their similarity. So reaction intermediates, the definition was in the previous note, reaction mechanisms and rate determining step. So reaction intermediates are produced and then consumed. I'm even going to shorten it just to produced and then consumed. And there's a variety of ways we can ask you this question. So here it says, if given the overall reaction. So it tells you A plus B makes AB as our reaction. So then you know there's no X's, so we're going to get rid of those substances. Anything with an X, right? So we're going to look, I'm going to use my blue, look for substances that are produced and then consumed. So AX is produced in step 1 and then consumed in step 2. So in, Hess's law or whatever, here it's a product, here it's a reactant. You would have crossed it out. And you would have crossed it out here because a known, you were right, because is AX in the overall? No. Okay? Now we have another substance, X, also a reactant and a product. So opposite sides of the arrow, we would have crossed it out. But we want to distinguish between AX and X. What's the difference? So a reaction intermediate like AX, you can even write that here if you want, was produced and then consumed, whereas X was consumed in step 1, but then it was reproduced or regenerated. We want to get the catalyst back. We want to be able to use it again. So it is not an overall reactant or product. However, it makes the reaction happen faster. And if you want, to be as useful as possible, then it logically makes sense. Yes, of course it has to be reproduced. We want to be able to reuse it. Okay? So reaction intermediates, produced, consumed, catalyst, consumed, and regenerated or reproduced if you prefer that. How else could we write this? Product and then reactant. Reactant, then product. If that makes more sense to you. Another little trick you could check. So even write also. You can have more than one reaction intermediate. You cannot have more than one catalyst. Or that makes no practical chemistry sense. And the last thing about catalysts, you do kind of have to remember from organic chemistry, and some of you asked me about it, you often would see things written over the arrow. And that is where we write a catalyst. So if you see something, the overall reaction, and it's got something over the arrow, then whatever's written over the arrow, that's the catalyst. So the rest of the worksheet, the questions, most of them ask you about mechanisms. What's the catalyst? Does it have a catalyst? And the questions from the textbook, again, the solutions are on the back of that page. It wants you to talk about the diagrams, what happens in a Maxwell-Boltzmann. So that's a good question too to take a look at. The solutions were tough for me to do. I tried to make it as obvious as possible for that Maxwell-Boltzmann question. I apologize that it's all on top of each other. Okay, so the rest of this is really just basically definitions. So you can divide catalysts into two categories, homogeneous and heterogeneous. And those terms, you would have used them in grade 9 science. It's the same thing. Homo means same, hetero is different. And really, the two categories come from the fact that catalysts are so useful. So homogeneous catalysts often are going to be aqueous. So the reaction has aqueous reactants, and the catalyst itself is aqueous, versus heterogeneous is usually solid and gas. So the catalyst is a solid, and the gas particles are attracted to it. So the categories really arise from what's the most useful practical thing here. So again, it says aqueous zinc chloride is used to catalyze this reaction. So you would see that over top of the arrow. So both reactants are aqueous. The catalyst is aqueous. So it's in the same phase as the reactants. Again, we're always concerned with the reactants here, just like before. And then heterogeneous catalyst is in a different phase. So the example we're going to talk about is hydrogenation. This would be a really similar idea to, like I said, a catalytic converter in a car. So they have to be in a different phase. Often that different phase is a solid and gas, like I said. So hydrogenation, again, if you're into health and eating well, then maybe you've heard the term hydrogenation, or changing fats into saturated fats, which is not good because remember they lie flat together and turn into fats, like waxy solids instead of oils. So you need a double bond, just like we did in the organic unit. And then what you're going to change it into is single bonds, okay? So usually, so without a catalyst, the reaction is very slow. So usually there's some kind of metal plate. I don't know why I always draw it as like a parallelogram. It doesn't really matter. And again, it's usually not a cheap metal, okay, like rhodium, gold, palladium, platinum. And what happens is the gas molecules are actually more attracted to the metal than they are to each other. So they're using a common name, ethylene. The gas, I don't know, so pick whatever you want. Let's make some symbols. They actually bond to the surface. And then the bonds are weakened. And once the bonds start to break, then the hydrogen can be added to the ethylene molecule because they are attracted to the metal. So the metal it provides the surface for the reaction to occur because the molecules are attracted to it more than they are to each other. So it increases their chance of colliding by providing a surface for the reaction to occur. And we always want faster reactions. You need more collisions. So then this is ethane here. If you want to draw it in symbols, you can. But you guys know this, right? We did double bonds and you add atoms to them and change it into single bonds. That's basically what this is. So addition reactions organic reactions often need catalysts. And then the opposite of a catalyst is what's called an inhibitor. So it reduces reaction rate by preventing the reaction from occurring. It can be a molecule like a preservative. A preservative is a chemical substance. It could also be even changing the temperature. We say that those inhibit the reactions, but in a chemical compound sense, then it changes the food. So even in medications, they'll use preservatives like phenol and stuff like that. So the opposite of a catalyst.